In this video, we'll explore the three famous Greek problems. Now, this image, called the School of Athens, represents some of the most famous Greeks that we know. And in the middle, you have Socrates and Plato. And one of the reasons is because Socrates was Plato's teacher, and Plato created the School of Athens, which helped create a lot of the mathematics that we know for the Greeks because they valued it so much in helping improve their thoughts on philosophy. Now, over 300 years, we have many achievements by the Greeks, starting with Thales and ending with Euclid. And through them came three different distinct lines of mathematical development. First, we have the Greek mathematics with the demonstrative that led through Euclid's Elements. And what we know about Euclid's Elements is that it's really a culmination of ideas and concepts that were created before Euclid that he put together into the Elements. Next, you have a group that started to work on limits and infinitesimals and summations that helped begin the concepts of calculus that are later credited to Leibniz and to Newton. And finally, you have the development of circles and straight lines and surfaces, and a lot of that came from the concepts that we learned from these three famous problems. Now, within Euclidean geometry, we often talk about the idea of using two different tools, the straight edge and the compass. And when we talk about the classic tools, the classic straight edge had no markings, no measurements, and could only make a straight line. The compass had no markings. If you picked it up, it just fell back in half, and it could generate a circle that we could define. So these three famous problems were famous because the Greeks could not solve them just with those tools. Now, these three problems, trisecting an angle, constructing a cube with twice the volume of a given, and constructing a square at the same area of a given circle, they can be solved, just not with the classic Euclidean tools. And it wasn't until the 19th century that we could actually prove this to be true. However, their quest in trying to solve these problems created a lot of mathematics that is used still today. So the first thing was the duplication of the cube, and this came about because a poet incorrectly stated that a cubical tomb with double the size would have double the dimensions, and that's just not true. So this problem was then brought to geometers in Greece and eventually came to Plato's Academy, where they examined it. And that is where Hippocrates came up with the idea of trying to come up with the doubling of the volume. So he said, let's start with two lengths, s, and double that, 2s. And if we use two mean proportionals and we split them apart, and we're going to use that x over y ratio to help us solve the problem, we cross multiply, and we get that x squared equals s times y, and y squared equals 2 times s times x. We want to rewrite the first one for y so that we can substitute into the second. And you get x squared over s. So I'm going to take that value and substitute it in here. And what that does is gives me x to the fourth over s squared. Now let's get all our x's together and all our s's together. And what you end up with is x cubed equals 2 times s cubed. In essence, the volume of one shape would be double that of the volume of the other. The problem here that you should see is that the length of each side then would be the cube root of each of these terms. Well, I can take the cube root of x cubed, but the cube root of 2 I cannot. And that's part of the problem, is that you cannot construct the cube root of 2 with a straight edge and compass. And so there are many solutions, like the one we just saw, that were created that would help you find the volume, but again, it could not be created just with the Euclidean tools. The next one was the idea that they knew that they could bisect angles, multi-sect segments, and so they wanted to be able to multi-sect angles as well. So let's look at a problem. Say we have triangle ABC, and I'm going to extend out ray DA so that I'm going to have a segment EF that's double that of AB. Now, if I connect and make the midpoint of EF, I get all these segments equaling 10. And what's nice about that is that I'll see that I have an isosceles triangle here, and I have isosceles triangles here as well. So AGE, this angle, will be equal to the doubling of these two angles. And I also know that AFG would be equal to EBC because of the fact that that is an alternate interior angle because these two lines are parallel. So what that means is that my angle here, ABE, is double EBC. In essence, I have trisected angle ABC. The problem here is there's not a way that I can construct EF so that it would be double BA. And to do that, you have to have a measured tool, and that's called the insertion principle. So if I have a marked straight edge, I could do it, but I can't without that marked edge to get me the double the length. Now, they are able to solve it, just not with Euclidean tools. For instance, Pappus used conics, and it also led to the creation of many different types of curves, such as the conchoid by Nicomedes and the spiral of Archimedes. So we know that trisection can be completed, but it requires either the insertion principle or it requires a cube root in a conics that cannot be created with Euclidean tools. So the last one is the quadrature of the circle. So what does this mean? It means that we're trying to create a square with the area equal to that of a given rectangle. Now, we can do the quadrature of a rectangle very easily. We start with a rectangle, we create a ray out from one side, then we're going to create a circle with this radius. Now we have BF, we find the midpoint, and now we create the circle using BG as the radius. We're going to take a ray up through DE, and you can see now, if I create a circle now HE, that creates point J and point H and point E. Those are 3 points on my square. So now I just need to create my perpendicular lines, and I have my square here, HKJE. And that has the same areas as BEDC. The question is why? So if I think about what I have here, G is the midpoint of BF. Well, BF is the same thing as saying BE plus EF, and we know that EF and ED are the same because we made that as a radius of this circle with center E. So what I can say is that BF is really BE plus ED. Now here's something that we have to think about then, is since I have this circle that goes up to H, I can create a right triangle where EH represents my altitude of my right triangle. And if you think back to the things we've learned in geometry, EH can create a geometric mean with BE and EF. So if I look at it, I could say that BE over EH equals EH over EF, or I could represent that EF with the ED, since that's part of my actual rectangle, and they are equivalent. Now if I do my cross multiplication for the proportion, and then I see I've got EH squared, so I take the square root, I know that EH, that length, is equal to the square root of the area of my rectangle. And because the square is length times width, and that's the square root times the square root, since they're the same, you take the square of a square root, it goes away, therefore that area is the same. So what I end up making is that the length is the square root of the area. So how does that relate to the quadrature of a circle? Well, the ideal is to create a square with the area equal to the circle, and it started as early as the Egyptians trying to figure this out. And here's the reason why you can't construct it with Euclidean tools. As I just stated, we know that the side of that square has to be the square root of the area that we were started with. Well, the area of a circle is pi r squared. Now I can take the square root of a number, such as r, it's going to be some value, and square root of r squared definitely gives me r, but pi is transcendental, and it cannot actually create, because it's irrational, with Euclidean tools. There's no way to construct that value. So because of that, we cannot do the quadrature of a circle because you can't construct pi. However, it did lead to many other creations, such as the lunes of Hippocrates. When he was looking for the quadrature of a curvilinear object, he ended up creating the lune, which is the outside of this semicircle created on the hypotentuse of a right triangle on a circle. And what he found is that that area of the lune is equal to the area of that right triangle made up of the two radii of the circle. So say I know that the radius of the circle is 4 inches, and I want to know the area of the lune. Well, I know that if I want to find the area of the triangle, which is equal to the area of the lune, I do 1/2 one leg times the other leg, because it's a right triangle. Well, I know each leg, because they're each a radius, would be 4 inches. So 4 times 4 divided by 2 is 8 square inches. So in this case, I know that the area of the lune would also be 8 square inches. Now, because they kept searching for this quadrature of circle, that's what led to the search for pi. And if we think about where pi has come from, civilizations have been searching for it since the Egyptians and Babylonians, where they started with 22/7, and even a couple other small, like 3 or 4 decimal places, were used by the Babylonians. Archimedes tried to use the idea of perimeters and inscribed or circumscribed polygons to create the boundaries. And you could see that as you increase the number of sides of your polygon, the closer and closer it would become to a circle. And that's called the classical method. And that gave us the approximation that we often use, 3.14. And then you start to see in the ADs breakthroughs in finding pi, to the point where in 1767 it was determined that pi was an irrational number by Johann Lambert.